Okay, problem to use mathematical induction to prove that x to the power of any non-negative integer it is 0. So you want to prove that this is 0, right? This is also 0. Like this is also 0. Like any positive integer it is 0. Okay, so we want to prove this is 0 for every non-negative integer. For every integer n greater or equal to 0. So what should we do? We should use mathematical induction, right? Induction is for you to prove when first step you need to prove when n is at the starting point it's true. When n is 0, it is true, right? When n is 0, this limit is right, it's just x to the power of 0 over e to the power of x. Right, then this part is 1, so it's just a limit of 1 over e to the power of x. X is approaching infinity, it is 0. Right? When n is 0, it is true. Okay, then the second part is if the statement is true when n is k, so this k is what? This k is an integer. This k is an integer. K is an integer. And k is greater or equal to 0. Right? Then what happens when n is k plus 1? So if you know this is true, then you know limit x to the power of k over e to the power of x equals 0. Right? Okay. If the statement is true when n is k, then you know this is true. Okay, then right. What about kx to the power of k plus 1 over e to the power of x? So here you can use one-step L'Hopital's rule. Right? It's just k plus 1 times x to the power of k over e to the power of x. Right? Then this part, right? This part is what we already know. Okay? So we can separate it to it's k plus 1 times this limit. Right? And this is 0, so it is 0. Right? So if this is true, then the statement is true. It's also true when n equals k plus 1. Okay. So if the statement is true when n equals k, it's also true when n equals k plus 1. Okay. Then by mathematical induction, you know that. Okay. And the conclusion is if the statement is true, for all integer n greater or equal to 0. Okay.